With the limits that we derived in the last couple of videos, we now have the tools we need to be able to use the limit definition of derivative to find the derivatives of sine and cosine. But before we do that, I want to take a graphical approach. I want to do something similar to what we did with exponential functions, which is just sketch our functions and sketch their derivatives and see if we can't make some sort of an educated guess about what we're going to get when we derive the formula. Excuse me. So I've got up here two pairs of axes. Here we're going to graph y equals sine x, and here we're going to sketch its derivative by going through and asking these questions. Is the graph going up or down? What happens at the transition points? And how steep is it? All right. Now I purposely have not filled in the graph of sine x. That's because if you have forgotten it, I want you to be experiencing a moment of discomfort right now. That's not because I'm a mean, horrible person, although perhaps I am. But the reason I want you to be feeling uncomfortable if you don't remember this is because that's a problem. And I want that discomfort to motivate you to solve that problem. If you do not remember what the graph of sine x or any of your trig functions looks like, you need to review that. And there are several ways you can deal with that problem. There's an appendix on trig in your textbook. There's also a link on our Canvas page to some additional trig resources. So there's a video on just the very basics of trig, and then I also linked to the videos I created when I was teaching trig during the semester that the pandemic hit. So they're the videos for the second half of my trig class, because the first half was actually in person. We used to actually go physically to school and meet in person and teach and learn. It was wonderful. I hope we return to that soon. All right. So there are those resources, and I've got office hours. I'm available by appointments. So if you don't remember what your graphs look like, that's a problem. Am I going to be mad at you? No. I want to help you. Okay? So you've got resources, you've got me, but deal with the problem. If a month from now you don't know what sine of x looks like, I'm not going to be very sympathetic because you've known for a while that it was a problem. Okay, so I want you to pause the video, sketch sine of x, and then try to sketch the derivative by just describing the behavior of this graph. All right, I've graphed y equals sine x here. I should probably label that. And here I just drew a picture of the unit circle to remind you how you can sort of double check things. Remember that when we're graphing sine, sine by definition is the y value that we get on the unit circle. So an angle of 0 would terminate on the positive x-axis. We start with a y value of 0. And then pi over 2, that terminates on the positive y-axis, where we've got a y value of 1. And hopefully you remember that sine and cosine just give us these waves, but you can always sort of double check if you're not sure which one starts at the origin. It's the sine graph that does. You should know that, but you can always confirm it here. Now, it is important that you indicated that it goes on forever. The domain of sine is all real numbers. So, it's a periodic function. It repeats its pattern over every interval of length 2 pi. So I know its derivative will be periodic too, because the derivative is just describing what it's doing. So if it does something, and then it does it again, I can describe it, and then I can repeat my description. Okay. So I really just need to sketch one period, but then I need to indicate that that's going to repeat and go on forever and ever and ever. Okay. So I'm going to just look between 0 and 2 pi. That's my standard period. And I'm going to ask those questions. Are we going up or down? Let me mark off my quadrantal angles down here as well, just lining things up. Okay. So it looks like we start out going up. And we go up until we hit this high point at pi over 2. And then we're going to go down. And we go down until we hit this low point at 3 pi over 2. And then we go up again. And it actually looks like we go up until we hit a high point which would be at my next quadrantal angle, which would actually be at 5 pi over 2. Okay, I think just to make things a little bit simpler, I'm going to observe that over here, where we're going up, we were sort of in the middle of a going up section. We were going up over here as well. I'm going to just extend over here and actually just draw a little bit more than one period so that I can sort of start and end at a high or a low point. Now, of course, what I know is that when the derivative is, when the function is increasing, the derivative is going to be positive. I'm looking for my yellow marker, which I use, here we go, to shade that. So where we're going up, the derivative will be positive. We'll be sketching above the x-axis. Where the function is going down will be negative. The derivative will be below the x-axis. And where the function is going up will be, once again, above the x-axis. Now, if we look at our transition points, the places where we change direction, are these sudden changes so that the derivative is undefined? Or are they nice, smooth, rounded changes so that the derivative is 0? Looks like they're all zeros. So now let's just start here and let's take a look at what happens with the steepness. We start out not very steep at all. We get steeper in the middle, but then we get less steep so that we can return to having a slope of 0 at that high point. So basically, if I label this as steep, not steep, steep, we bump up to get, not super steep, but steeper. We bump up and then we come back down. Same thing here, not very steep. We get steeper in the middle, then we get less steep again. So we're going to bump down to be moderately steep and then come back up to 0. And then again here, we're just repeating this pattern. We get steeper in the middle and then we get less steep again. Now that's actually a period and a half of the derivative, but now it's just going to continue. Since this function continues, its derivative continues. So if I look at what we have in just that first period going from 0 to 2 pi, it looks like we're starting at about a high point. We've got a wave like so, and coming back to approximately a high point. Do I know a function that does that? I do. This looks an awful lot like the graph of cosine. Now, this doesn't prove that the derivative of sine is cosine, because I do not know that the high point is at exactly 1 and that the low point is exactly at a height of -1. I don't know that the curvature of this thing exactly matches the curvature of cosine. But based on this, I would say that guessing that the derivative of sine is cosine would be a reasonable and educated guess at this point. And in the next video, we'll use the limit definition to either confirm or disconfirm, deny, or confirm or not that guess. Okay.